This topic is about roots of polynomial equations. We start by looking at quadratics, but all of the results that we're going to discover apply in a slightly more generalized form to cubic equations, quartic equations, and so on all the way up the line. There are some really important ideas behind the scenes here that will tell us about how roots of equations are connected to each other, and we'll be able to do a surprising amount without even calculating the roots themselves. I'm going to start with this statement that you will probably disagree with initially. A quadratic equation will always have two roots. What do I mean by that? Well, we had a whole topic on quadratics at the very beginning of A-level Maths, where we talked about the discriminant and how we could tell whether a quadratic has two roots or not. And sometimes it does, and sometimes it only has one, and sometimes it has none. But that was back when we were dealing with a one-dimensional number system. Remember those happy times, simpler times, when all your numbers lay on the same line? Well, if you're talking about real numbers, then yes, you could say sometimes a quadratic doesn't have any solutions. But now we've got complex numbers to work with, we have a bit more flexibility. The quadratic equation may not be solvable for real number solutions, but it absolutely can be solvable for complex number solutions. So maybe our discriminant test shouldn't be saying positive discriminant, two solutions, negative discriminant, no solutions. Maybe it should be saying positive discriminant, two real solutions, negative discriminant, two complex solutions. And then the only pesky bit in the middle is what happens with a zero discriminant. And we can deal with that quite nicely by deciding to treat our repeated roots as two roots that happen to be the same. And that's essentially what's done in the fundamental theorem of algebra. It states that a polynomial of order n has n roots, always. And the only way that can work is if we decide to count repeated roots as multiple roots that just happen to be equal in size. So a quadratic like x minus 3 in a bracket squared equals 0 has two roots. They just both happen to be the number 3. So now we've got that new definition, and we can think in terms of two roots that are possibly equal and two roots that are possibly complex rather than real. Well, we can now start thinking more generally about any quadratic. We stick with quadratics that have real coefficients. So a real number in front of x squared, a real number in front of x, and a real number tacked on the end. But they could very well have complex numbers for their roots instead of just real numbers. But you're already thinking probably, why are we talking so much about the roots instead of just finding the roots? We learned how to find the roots of quadratics a long time ago. So if it's so straightforward to calculate them, why do we need to do other things with them? Well, the reason is we can't necessarily calculate the roots so easily with a cubic equation or a quartic equation. You can look up the formula for a cubic equation if you're curious. It's complicated. And there is a method for solving quartic equations, but it's been proved that there is no possible formula for the general quintic equation, and anything above order 5 we can't solve directly unless there's a trick, unless there's some nice simplification you can make. If you've got x to the power 5 equals 32, for instance, you're probably going to be able to solve that one, but in general you're going to struggle to solve anything of order 5 or more. And yet we still need to be able to deal with them, work with them, interact with them, possibly generate new versions of them whose roots are related to the original polynomial's roots. And that's where these results we're going to investigate come in really handy. So we can work with them even if we can't find them, the roots. Let's start by looking at these two. These are both the same quadratic equation, but I've written them in a general format so that we're not going to be bogged down by a specific case. Ax squared add bx add c equals 0 is what you might call the standard format for a quadratic. You'll have seen it in the quadratic formula statement. If you have roots of a quadratic being written as negative b plus or minus root b squared minus 4ac all over 2a, then that's because we're using the ax squared add bx add c format for a quadratic equation. The calculator also has this. If you ask it to solve quadratic equations for you, then it will have this up on the screen and you're just entering the values for a, b, and c. Now the other one may look a bit less familiar. because I've got an alpha and a beta in there, but it's essentially a way of demonstrating that any quadratic can be factorized. And again, this may fly in the face of what you originally learned about quadratics, but that's only because when you were first told this quadratic can't be factorized because it's x squared add 1, what we meant was this quadratic can't be factorized with real numbers. Or even earlier than that, maybe this quadratic can't be factorized with nice numbers. If I had x squared minus 2, well, you now know that you could factorize that as x squared plus root 2 times x plus root 2 times x minus root 2, the difference of two squares. But the only issue is, because the roots are quite awkward, it'll be a hard one potentially to factorize for yourself. Even worse if the roots are something like 3 plus root 7 all over 4, and 3 minus root 7 all over 4. But since any quadratic has two roots, it must be possible to factorize a quadratic into two brackets. Even if those roots happen to be complex numbers or irrational numbers, that doesn't matter. We can theoretically write them as two brackets. And what we're going to look at now is how we can reverse engineer those so that we can find a link between the coefficients a, b, and c and the roots alpha and beta. So I'd like you to give it a go first. Pause the video and expand the brackets and see if you can find some sort of connection, write an equation that links alpha and beta with a, b, and c. When you're ready, unpause and we'll continue. So here's what you should get, something like this. When we expand the brackets, x squared minus alpha x minus beta x plus alpha times beta. And if you group it a bit more nicely, you'll be able to more easily compare it to ax squared plus bx plus c. But there's another thing that you might have noticed. When you expand the factorized version, you get a single x squared. It's called a monic quadratic because it's a 1x squared. We've got one that isn't. It's got an ax squared. But we can very easily convert that to a monic by dividing everything by a. We get x squared plus b over a x plus c over a equals 0. And if we do that, well, all you need to do then is recognize that the number at the end, the plus alpha beta, corresponds to the number at the end, which is now not just c, but c over a. And similarly, we've got a number in front of x, that's minus alpha plus beta, and that corresponds to the number in front of x, b over a. So being a little bit careful with the negative sign, we can generate for ourselves a couple of useful results. We've got the sum of the roots is always equal to negative b over a, and the product of the roots is always equal to positive c over a. And that will work for any quadratic you like. And it doesn't matter if you can easily find the roots. It doesn't matter which quadratic you have, whether the roots are real or complex. Those results are always going to be true. They are known as Vieta's formulae. You can look that up online if you want to find out more about it. And you can see the more generalized versions of those when we get onto cubics and quartics and so on. They follow very, very similar patterns. So once you learn this one for quadratics and recognize where it can come from or recreate it as needed, doing the same thing you just did, then you'll be able to easily generalize that to the order 3 and order 4 case and so on. So now we're going to look at how we can use those formulae. And one of the most common questions you might be asked for this is, can you create a new equation which is related to an old equation? You'll be provided with an equation, maybe a quadratic, maybe a cubic or something else, and you'll be asked to generate a new one whose roots are twice the size of the original roots. But to do all of that without ever bothering to calculate the roots themselves. Let's try it. We've got 2x squared add 3x add 4 equals 0. And its roots we're just going to refer to as alpha and beta. And if you're anything like me, you'll be tempted to jump straight to a calculator and find the roots of that quadratic. And feel free, go ahead. You will find that they're a bit awkward, basically. They will be complex numbers, I believe, in this case. And so although you could calculate those roots and then you could double them and then you could work backwards to generate a quadratic equation who has those roots, you'll probably find that it's quicker and easier to follow the process that we're going to do here. And even if it wasn't, this process would still be worthwhile because we'll be able to apply a very, very similar one to cubics and quartics and so on, where finding the roots is by no means as simple as for this particular case. We start like this. We're looking for a quadratic equation whose roots are double the original quadratic equation's roots. So I'm going to write them like this. We have 2 alpha and 2 beta. Now this can get confusing because when we think of alpha and beta as the roots of a quadratic, but we're dealing with 2 different quadratics in the same question, we have to be a little bit careful with our notation. The first thing I would do is start with the original quadratic you're given, and you find the sum and the product of the roots. So we add alpha and beta, and we know from the formula that we're given in the blue box that alpha plus beta will have to be minus 3/2. And we also know from the formula that if you multiply the 2 roots, you should get c/a, which is 4/2, which is 2. So even though the roots might be horrible, complicated, complex numbers, if you add them together, you get a nice straightforward answer, minus 1/2. And if you multiply them together, you get a nice answer, 2. We'll talk a bit more later about how it's possible for complex numbers to both add together to give a real answer and multiply together to give a real answer. We will come to that, but for now, we're going to continue and we'll just be grateful that it does give us nice numbers. The next step is to calculate the sum and the product of the new quadratic's roots, given what we know about how it links to the old quadratic's roots. So here's how I'm going to do this. I'm going to add 2 alpha and 2 beta together. This is the sum of the roots of the new quadratic. But then I'm going to notice that 2 alpha plus 2 beta can be rewritten pretty easily as 2 lots of alpha plus beta. And here's the clever bit. We don't know what alpha is, we don't know what beta is, but we do know what alpha plus beta is. So there's no need for me to ever calculate alpha or beta to generate the sum of the roots of the new quadratic. And a similar thing happens over here when we have the product of the roots, 4 lots of alpha beta. We're doing 2 alpha times 2 beta, we get 4 lots of alpha beta. And alpha beta, we know. We don't care what alpha is, we don't care what beta is, we know what the product of alpha and beta are, and that gives us our answer. So now we know that the sum of the roots of the new quadratic is minus 3, and the product of the roots of the new quadratic is 8. The next step is to use Vieta's formula again, and we work backwards this time. We've got the sum and the product of the roots. We need to try to work out A, B, and C. But you'll notice something here as well. We've got 2 equations and 3 unknowns that we're looking for, A, B, and C. That isn't actually so much of a problem as you might think, because we've got a bit of flexibility. 2x squared add 3x add 4 equals 0 has certain roots. But if you think about it, 20x squared add 30x add 40 equals 0 has the same roots. So A, B, and C could be scaled up and scaled down without affecting the roots of the quadratic. It would absolutely affect the shape of the graph. If you multiply all of the coefficients by 10 and then you draw the graph of y equals the quadratic, it would stretch the quadratic vertically by a scale factor 10. But it wouldn't affect the roots of the quadratic because at those points the y value is 0, so stretching by a scale factor 10 maintains the 0 value. What that means for us is that there are many quadratics whose roots are double the original roots. Some of them are very stretched out and some of them are very low and flat, but they all cross at the same place on the x-axis, if they cross the x-axis at all. They cross some kind of complex plane. Well, it's harder to visualize, but the logic is still the same. It doesn't matter how they're scaled as long as they have the correct roots. That's why in the question, it doesn't say create the quadratic whose roots are double the original roots. It says a quadratic. Find a quadratic equation whose roots are 2 alpha and 2 beta. So let's see what this looks like. These a, b, and c down here refer to the new quadratic. We have minus b over a has to equal negative 3, the sum of the roots of the new quadratic. And we have positive c over a must be equal to 8, because that's the product of the roots of the new quadratic. And then because we're allowed any scaled up or down version of our quadratic, generally speaking at this point, we just choose a suitable value for a. So there's no necessity here to have A be anything in particular. Sometimes a question will ask you to write your final quadratic equation in the form ax squared plus bx plus c, where a, b, and c are integers with highest common factor 1, or something like that. In other words, try to make sure it's in its simplest form, something relatively nice. And in this case, it makes perfect sense to set a equal to 1, because negative b over a and c over a both come out as integers. They're pretty nice, and they don't have any common factors already. So making a equal to 1 allows us to find a value for b and a value for c, and to generate the quadratic equation that we need. X squared add 3x add 8 equals 0. If you'd chosen to make a equal to 2, you'd get another perfectly valid quadratic. 2x squared add 6x add 16 equals 0. And that will be fine as well. Now you try one. We have a quadratic equation. Again, it's going to be a bit of a messy one. If you want to find the roots for yourself and verify, then you can. But we should find it easier to generate the new quadratic completely sidestepping the calculation of roots than it would be to find the roots and use them to generate the new quadratic. We have 5x squared minus 4x add 10 equals 0, and you're asked to find a quadratic equation whose roots are just 3 higher than the original roots. These are the steps that we used last time: finding the sum of the products using the formulae, calculating the sum of the products of the new quadratic's roots, and then using the formulae once more to work backwards from those to the coefficients of the new quadratic. And remember, you can choose whatever the most convenient value of a is, so that you make sure you get nice whole number values for a, b, and c. Pause the video, give this a try, see how you get on, and then come back and compare. All right, step 1. Alpha plus beta, we know is minus b over a. We can substitute those numbers in, we get 4/5. Alpha beta, similarly, we get a value of 2. Now, if we're looking for the sum of our roots for the new quadratic, we're going to need to add together alpha plus 3 and beta plus 3. You'll notice now, this is an alternative that you might like to use. I've started to employ a subscript, alpha 1, beta 1, because that way I can talk about the roots of my new quadratic and the roots of my old quadratic in the same line without worrying about there being confusion or ambiguity between the alphas and the betas. But if I add those, you can see that the 3's can just be added on at the end, and the rest, the alpha plus beta that I already know, can just be substituted directly in. So that makes life nice and simple. We can do the same kind of thing for alpha times beta. The product of the new roots, alpha 1, beta 1, I've called it, will be alpha plus 3 times beta plus 3. Now this one's quite nice, because when you expand it out, yes, you can group an alpha plus beta, and we know the value of alpha plus beta, we've mentioned that already, but there's also an alpha beta term, and for that one we're going to need the 2. So we end up using both. We get the 2 from the product of the roots, and we get the 4/5 from the sum of the roots. And if we put both of those in, we can calculate the product of the new roots. It comes out as 67 over 5. And the final step, we go back to the formulae, and we're now finding the values of a, b, and c. I suppose you could call these a1, b1, and c1, but it's far enough down the question that I think it'll be fairly clear from context. So I'm not going to worry too much about that. We get to choose our value of a, remember. So you might be thinking of a value of a right now that's going to work nicely. Hopefully you thought of the same one as me. I'm going with a equals 5 because that will allow us to deal with those fractions quite nicely. If a is 5, then b will be negative 34. Take care with your minus signs. It's a very easy one to get mixed up on here. And c will be 67. So we get 5x squared minus 34x plus 67 equals 0. Here's another one to try. We're starting with the same quadratic, and I've put the 3 steps up for you. So I'd encourage you to pause here and have a go at finding a quadratic equation whose roots are the reciprocals of the roots of this quadratic. Okay, let's start with step 1. The sum and the product we know already. We did that last time, so I'm going to assume we got the same numbers. For step 2, we need the sum and the product of the new quadratics roots. So we have to find alpha plus beta when alpha and beta are now 1 over the original alpha and 1 over the original beta. So I'll call them alpha 1 and alpha 1 and beta 1. And I'm going to start with the product because that seems the simplest. If you're going to multiply those two fractions together, then hopefully you'll spot pretty quickly out pops the product of the roots and we get a 2. Therefore 1 over 2. When we look at the sum of the roots, there's a bit more work to be done, but we can add fractions together. And when you get into the swing of this particular topic, you'll start to enjoy the process of trying to manipulate an expression so that you can write it exclusively in terms of things you already know. In this case, in terms of the product of the roots and the sum of the roots. It's perfectly fine to have both appearing in the same place. We had that last time as well. Because we know alpha beta and we know alpha plus beta. And we never need to find alpha or beta independently. All we need is something related to them. And that gives us the sum of the new roots. The last thing we need to do is use Vieta's formulae once more. And we can go back. You've got to check carefully. When I did this the first time round, I ended up getting these values the wrong way around. Because if you've calculated the product before the sum, like I did, then maybe you just get them mixed around. Minus b over a is the sum of the roots. We can see that up here. So we need to remember that the sum of the roots is the one we need for that one. And then for c over a, we want the product of the roots. That gives us a half. Then, remember, we get to choose a suitable value of a. Would you pick 1? Would you pick 2 or 5? In this case, the best choice, if you want to end up with a quadratic with integer coefficients, is actually 10, the lowest common multiple of 2 and 5, so that it will give us a whole number value for b and also for c. So I choose a equals 10. That gives me a b value of minus 4 and a c value of 5. 10x squared minus 4x plus 5 equals 0. And remember, you can solve the original quadratic equation and solve the new quadratic equation on your calculator, compare the roots. But this time, comparing the roots will be a little bit more awkward because they'll all be complex numbers and you'll have to do the reciprocal of a complex number and see if it matches the other complex number you've got. There is a complex number calculation mode on the calculator, but it's still fairly tedious and long-winded. So as a method for finding the quadratic equation, it's not the most efficient. And generally speaking, in the exam, they're testing you on this particular technique, these particular ideas. So they're going to ask you to use these approaches rather than finding some other way around. And of course, most of the way they do it is by giving you something like a cubic or a quartic equation, so that you're applying the same techniques, which is a little more sophisticated than what we're doing here, but very similar ideas, but obviously a lot harder to independently verify by looking at roots. Now you should be able to have a go at the first few questions from exercise 4a in your Pure Core 1 book. When you've done those, or had a go at them at least, and you've identified which bits are confusing, then I'm going to go through a few of the later bits of that and set you up for the next few questions. All right, if you've finished those 3 questions, you might have found yourself a little bit stumped by the one involving the cubes of alpha and beta. I know I was confused by this when I first came across it. It took me a long time to make sense of how I could possibly find a way of rewriting alpha cubed plus beta cubed in terms of the sum and the product of alpha and beta. But there is a helpful hint in the book, so if you use that hint, you might well have got a bit further than I did originally. The sum and the product of the roots we can generate the same way we have. I've stuck with the same quadratic I had before to make life easier here. And then the sum and the product of the new roots, we're going to need the sum of alpha cubed and beta cubed and the product of alpha cubed and beta cubed. The product is going to be simple because we can pull out that power of 3 and we get the product cubed, which is just 2 cubed. The sum, a little bit trickier. How can we rewrite alpha cubed plus beta cubed in terms of alpha plus beta or alpha beta? Well, it's not the same as alpha plus beta in a bracket cubed. If you stop and think about it for a second, you will see why that has to be the case. If you expand alpha plus beta in a bracket cubed, you get something completely different. because there are all the annoying middle terms. However, if you expanded that, you would have found something useful. We don't just get alpha cubed plus beta cubed, but we do get alpha cubed and beta cubed. We also get some other things. So stick with it, persevere, and see if you can rewrite it in a slightly different way. Turns out you can pull out a common factor. Those middle terms there, 3 alpha squared beta and 3 alpha beta squared. You could pull out a 3, of course, but you can also pull out a common factor of alpha and a common factor of beta, leaving you with alpha plus beta. So that's quite handy. And I've then rewritten to make the alpha cubed plus beta cubed the subject, because that's the bit I have, and I want to rewrite it in terms of the rest. But you'll see now that what I've got on the right-hand side of my identity, I suppose you'd call it, on the right-hand side, we've got something that only involves the sum of the roots, alpha plus beta, and the product of the roots. So we've got alpha plus beta in a couple of places, and we've got the product alpha beta in one place as well. So we can use that. Over here on the right, we've got the sum giving us alpha plus beta cubed minus 3 alpha beta alpha plus beta. Chuck all the numbers in, we get our result. It's a bit messy, but it's not the end of the world. The final step, we choose carefully a value for A that will allow us to find a value for B and C, so that we've got nice whole numbers for the coefficients of x squared, x, and the constant. So I'll pick A equals 125 because one of our fractions there has a denominator of 125. The other one's not a fraction at all, so that's fine. And that will be the quadratic we get. Again, if you want to test it by finding the roots, then you can, but it's a lot quicker and simpler when they've got horrible complex roots like these to not. If you want to practice, make a quadratic for yourself that's got nice roots, and then you can test it and go back and forth. And a lot of the ones in the book you'll be able to do like that. So I'd encourage you, while you're developing your confidence with it, to try the result you get at the end, the result you had at the beginning, and compare the roots for yourselves. Maybe sketch them on GeoGebra and see what they look like compared to one another, and whether the roots appear to have done what this suggests they should have done. So the result we've just looked at is actually the more complicated of two results. The one above, you might have recognized you could have made use of it already. If you've got alpha squared plus beta squared, you can generate that by thinking of what happens when you expand alpha plus beta in a bracket squared. The middle terms, the bits involving alpha beta, they're actually not a problem. We just need to take them into account because we know the product of the roots as well as the sum of the roots. When we get to cubing them, we have to be a bit more sophisticated, but we can still pull things out. So those are really handy to have in your consciousness somewhere. You don't need to memorize them as such, but I'd highly recommend you get into the habit of thinking when you see the sum of the squares or the sum of the cubes of the roots, think to yourself, there's something useful here that I can get by expanding the sum of the roots squared or the sum of the roots cubed. And then you can work them out for yourself. Now we're going to look at a few more patterns we can see. Is there anything else we can say for sure about the roots of a quadratic, even if we're talking in the general case where we don't have particular information about exactly what the roots are? So let's start by thinking about a general quadratic equation, again with real coefficients. We always stick with real coefficients during this topic. You can work with quadratics that have complex coefficients, but some of what we're about to say doesn't apply when the coefficients are complex numbers. So we're talking about quadratics that you get where A, B, and C are all real. And we know, therefore, that the sum of the roots has to be real, because we already know that it's minus B over A. And B and A are both real numbers. If you divide a real number by a real number, you get a real number. The only exception will be if you're dividing by 0, but alpha A in this context is not 0 because we're dealing with a quadratic. If A was 0, it wouldn't be a quadratic. We also know the product of the roots has to be real because that's C over A, and C and A are real numbers. So now we've got a bit of a conundrum. If alpha and beta are complex numbers, what makes us think they're going to add together to give a real answer? And simultaneously, they need to be able to multiply together to give a real number. two complex numbers that have a real sum and a real product? Well, if you want to have a think, I recommend you pause the video for a minute and have a ponder about what these numbers might be. Can you come up with any complex numbers? They have to be complex, not purely real, but complex numbers that when you add them, you get a real answer. And also, if you multiply them, you get a real answer. Right, how about complex conjugates? How can we make use of that complex conjugates idea to help us out here? Well, if you've forgotten what complex conjugates are, quick reminder, we usually use a little star. So if you've got Z and Z star, then Z star is the complex conjugate of Z. And of course, Z is the complex conjugate of Z star because the conjugate of a conjugate is the same thing. So it works in a sense a bit like negatives, but it's not the same as a negative. If you put a negative in front of a complex number, then you make the real and the imaginary components both change direction, change sign. So you end up with your the vector, if you like, representation on the Argand diagram pointing in the exact opposite direction. But if you apply the conjugation method, then all you're doing is changing the imaginary component. So A plus BI becomes A minus BI. And you might already be noticing why it makes sense that they would have a real sum. If you add them together, the imaginary bits completely cancel out and disappear. We have two A's from the real part of both added together, but BI and negative BI disappear to give us no imaginary part. If you add two complex conjugates, the imaginary parts always cancel out because they're equal in size but opposite in direction. But what about multiplying? Turns out, a bit more work, but if you multiply two complex numbers together and they happen to be complex conjugates, then we get a kind of difference of two squares thing going on. A plus BI times A minus BI will end up with A squared minus B squared I squared. But I squared is -1. So if you're taking away negative B squared, you're adding B squared. So it's a bit of a weird difference of two squares, but that's effectively what's going on. And although A and B don't, in the sum, B disappears and it doesn't matter what B was, it doesn't affect the value of the sum. But in the product, both A and B are relevant. And yet we still get a real term, a purely real number here. You might recognize the A squared and B squared. You might be thinking, well, that's related to Pythagoras. It somehow links to the size of the original numbers. And that's worth thinking about. If you find the modulus of alpha, you get root A squared add B squared. And the modulus of beta is the same, root A squared add B squared. So this is the square of the size of either alpha or beta. And that shouldn't surprise us, because if you multiply two complex numbers, you multiply the moduli. There we can see it. Provided alpha and beta happen to be complex conjugates, the sum is real and the product is real as well. Now that's what we call a proof of sufficiency, which means I've demonstrated that it is sufficient for alpha and beta to be complex conjugates, but I haven't shown that it's necessary for them to be complex conjugates. I've given you an example of a pair of complex numbers that have a real sum and a real product, but I haven't demonstrated that that is the only possible example. If you're curious, they are the only possible way that it can work, and we'll go into that at the end of the video in the bonus section if you stick around for that. For now, you can know that they work and that nothing else does, and that we could demonstrate that should we need to. It's worth thinking about the Argand diagram at this point as well, because we can work through this with A plus BI, the rectangular form, but if you think about the argument of a complex number and the argument of its conjugate, you might notice something nice in there related to what we talked about in that second chapter on complex numbers. So in general, this is a rule that you can take to the bank. If you've got a quadratic equation with real coefficients, then it is always true to say that the roots are either real themselves, possibly equal, possibly not equal, or if they're not real, then they must be complex conjugates. Both of them complex numbers and conjugates of one another. Never get a real quadratic equation with only one real root and one complex root. If you get a complex root at all, then you get two complex roots. And if you know one of them, then you know the other one because it will be the conjugate of the one that you know. You'll find that fact useful when you're answering some of the later questions. So you can have a go at questions 4 to 10. And if you know one of the roots of a quadratic equation and it happens to be a complex number, then you can quickly and easily write down the other root because it will always be the conjugate of that complex number. If you want to try some of the later questions as well, feel free. I'm going to go through question 11 as an example next. So when you've had a go at the questions on here, if you want to try question 11 before I go through the example, you can do that too. All right, we're going to look at this one because it's a slightly different format to some of the earlier ones. We're still making use of the same results, so it's just a case of keeping track of the A, B, C, alpha, beta, and in this case M and K, and using the information that's been given. We've got a quadratic equation that involves M, and then we know something about the roots, but really all we know about the roots is that one of them is double the other one. But apparently that is enough information for us to identify the values of both M and K. Well, in order to do that, we're obviously looking for a connection between the coefficients of the quadratic equation, because in this format, it's all about the coefficients, m, 4, and 4m. But also, we've got the roots of the form k and 2k. So we know from that description, we need some link between coefficients and roots. We know we're going to be using Vieta's formula. So step 1, let's find the sum and the product of the roots. And this will give us results in terms of m, because the sum and the product of the roots from the original standard format for a quadratic will all be in terms of a, b, and c. So we'll get our values in terms of m. After that, we can use the information given in the question to write the sum and the product of the roots in terms of k. So they've told you that the roots are k and 2k. You could add them, you could multiply them, and that will give you the sum and the product, but this time in terms of k. And then the last step will be to marry those two things together. You've got information about the sum of the roots in terms of m and also in terms of k. And since the sum of the roots is equal to the sum of the roots, those two things must be the same. The same applies to the product, so you could put them together. If you've not yet tried this question and you want to pause at this point, now you've got a bit of structure, give it a try. Then you can unpause and we'll go through it together. Step 1. If you add alpha and beta, that should give us something equal to minus b over a. That is the result that we're going to be using. And that means that alpha plus beta, the sum of the roots, must be minus 4 over m. And you can do a similar thing for the product. Alpha beta must be 4m divided by m. So that one actually simplifies to 4. It may still be simultaneous equations, but it'll be the sort where one of them is easy to solve because one of the variables doesn't appear in it. Step 2. All we're doing here is saying the roots we've been told are k and 2k. So the sum must be 3k and the product must be 2k squared. So that's nice and simple as well once we recognize what to do. And the third step, we link these together. So we've already said that the sum of the roots is minus 4 over m. And now we've said the sum of the roots is 3k. So these two must be the same. And similarly, if the product of the roots is 4, and the product of the roots is 2k squared, then 4 is 2k squared. We can create for ourselves an equation for each of those results that we've noticed. And then we can solve. Be a little bit careful here. K squared equals 2. Don't just jump to root 2. Even though the question says find the values of m and k, and in a real exam, chances are they would word it a bit more carefully than that. In the textbook, you should probably be expecting the occasional poor wording or the occasional mistake, because that's how it works when you've got hundreds and hundreds of questions. So be a little bit skeptical potentially. If you think there's going to be 2 results, even though the question didn't really imply it, then go with the 2 results. Maybe check the answers afterwards to see if you were right, but in this case, that's what they're expecting. Once you've got the value of k, and you only need one equation for that because m doesn't appear in the second equation, then we can substitute that into the one on the left and we can find the value of m. Now you'll notice I've used that weird minus plus sign instead of a plus minus sign. And that's because for this, we need to make sure that when k is positive root 2, m is going to be negative 2 root 2 over 3. And when k is negative root 2, m is positive 2 root 2 over 3. You might recognize that minus plus sign from the cos a plus or minus b formula from the formula book. So it's still, in some sense, just telling you that it's either positive or negative, but it's also telling you when it's positive and when it's negative relative to other things on the same page, if you like. So we then make it crystal clear which one goes with what. We say either we have k equal to root 2, and then m would have to be minus 2 root 2 over 3, or k is negative root 2, and m would be positive 2 root 2 over 3. So watch out for that little detail. This final section is just to tie up the loose ends. We demonstrated that it is sufficient to have complex conjugates if you need the sum and the product of your two numbers to be real. We didn't yet demonstrate that it is necessary to have complex conjugates. In order to show that every time you need a sum and a product to be real, the only possibility is that your two numbers are complex conjugates. That's what we're going to try to demonstrate here. We're going to start by looking at a quadratic equation with real coefficients, and all we're going to assume from the beginning is that the sum of the roots alpha and beta has to be real based on the results that we've seen, and that the product of the roots must be real. Can we derive just from that the sum of two numbers is real and the product of the two numbers is real? Can we demonstrate that the two numbers have to be complex conjugates if they're complex? Well, we're going to start by writing our roots like this. But I want to point out briefly at this point, if we don't know anything about alpha and beta, we don't know if they're going to be purely real numbers or not, then it's still safe to write them in this format, because it might turn out that alpha is actually negative 3, in which case that's not a problem. A1 will be minus 3 and A2 would be 0. So that's going to be fine. If alpha and beta turn out to be real numbers, then that's not a problem for us. We'll just get the imaginary components, A2 and B2, dropping out and becoming 0. If, on the other hand, they end up being complex conjugates, I'm expecting that A1 and B1 will have to be the same, and that A2 and B2 will have to be the negatives of one another. So let's see what happens. We calculate the sum and the product. I do the sum first because that's easiest. We add the two real components to get the real component. We add the two imaginary components to get the imaginary component. Then we do the product of the roots. And you've got to be a little bit careful with this, and I've skipped out a line or so you might want to try this for yourself. When you multiply the two, there'll be 4 terms that come out. The very first term is the two real bits multiplied, so that's definitely real. That's the A1, B1 at the beginning. The very last term is also real because it's got too many i's not to be. A2i times B2i is going to be A2, B2, I squared, and the I squared becomes negative 1. That's where that real component comes from. The two middle parts are where you have a real component like A1 multiplied by an imaginary component like the B2i section. So we get A1, B2 and A2, B1. Both of those are imaginary pieces, so they've been multiplied by I. Now, remember what we said. If we want the sum to be real and the product to be real, then really that's another way of saying these numbers we've got written here need to have a 0 imaginary component. We're basically saying this bit needs to cancel out and disappear, and this bit needs to cancel out and disappear. Well, let's start with the simpler one. A2 plus B2 would have to be 0. And then the other one, A2, B1 add A1, B2, would also have to be 0. What does that tell us? Well, for the first one, if A2 and B2 add together to give 0, then A2 is actually going to need to be equal to negative B2. So whatever A2 is, B2 will be the negative of it, and vice versa. Well, we can actually substitute that into the second equation and find out something more. I've replaced A2 with negative B2. And then once I do that, I can pull out B2 as a common factor. And after I do that, I've got something which is factorized and the product is 0. And this result works just the same with complex numbers as it does with real numbers. If you've got two numbers that multiply to make 0, then you've got two possibilities. Either the first factor is 0 or the second factor is 0. So either b2 is 0 or a1 minus b1 is 0. Let's look at both of those in turn because they're both equally valid ways of making this work. Maybe b2 is 0. Well, if b2 is 0, look back here and you'll remember that a2 is equal to negative b2. So if b2 is 0, then a2 is also 0. And b2 and a2 are the imaginary components from way back at the beginning. They were the pieces in front of I. So in this particular case, alpha and beta are just a1 and b1. There's no I component. What about the other option? What if the bracket a1 minus b1 is actually 0? Well, if that's the case, then a1 would have to equal b1. And if a1 is equal to b1, and remember, without changing anything, I'm just restating the result we had before, a2 is also necessarily equal to minus b2. Now, what does that tell us? It tells us that the real components of alpha and beta must be the same, and that the imaginary components of alpha and beta must be the opposite sign. That is exactly the definition of complex conjugates. So we've demonstrated now that if the sum of your two numbers is real and the product of your two numbers is real, then only two things are possible. Either you're dealing with two real numbers, purely real numbers as opposed to complex numbers, or you're dealing with complex numbers which are also complex conjugates. They're the only possibilities. Another nice way to convince yourself of this, that I think is in some ways more convincing on a visceral level because it's less reliant on algebra and more reliant on spatial geometrical reasoning. My alternative argument here involves the arguments of the complex numbers. Remember, that means the anti-clockwise angle made with the positive real line. So you can see in the animation we've got a complex number represented being dragged around and its complex conjugate, which is essentially a reflection in the real line. Because the real component's always the same, the imaginary component is the exact negative. If we write our complex number in modulus argument form, r times cos theta plus I sine theta. Remember, this just means a complex number with a size, a modulus, of r, and an argument, an angle with a positive real line, of theta. If we do that, then the conjugate has to be r cos theta minus I sine theta. We've just got a negative sign in there because the imaginary component is the negative of what it was. But we can use a bit of a trick here, and we kind of need to because it's not in mod arg form yet. If we wanted to write it in modulus argument form, we would need to deal with that minus sign. It should be cos of something plus I sine of the same something. And when it is, then we can read off that something and say, well, that must be the argument. Here's what we're going to use. The fact that cos theta is a symmetrical graph. It is an even function, if you like, which means that cos of theta and cos of minus theta are the same. And sine is an odd function. Sine is not symmetrical in terms of mirror symmetry in the y-axis, but the sine graph does have rotational symmetry about the origin, which means that sine of minus theta is equal to minus sine theta. That is to say, a reflection in the y-axis for sine theta is equivalent to a reflection in the x-axis. If you think about the sine wave, y equals sine x becoming y equals sine of minus x would represent a horizontal stretch of scale factor -1, which is equivalent to a reflection in the y-axis. But if you have y equals minus sine x, that is a reflection in the x-axis from y equals sine x. But those two both give the same thing, which means sine of minus theta could be used instead of minus sine theta. And cos of minus theta could be used instead of cos theta, and that's exactly what we do here. Now, alpha star, the conjugate of alpha, is written in mod arg form, and we can directly read off the argument. It's written in the right format, which means that we know for sure the argument is minus theta. And you'll notice the modulus is still r, the same size. So the conjugate has the same modulus, but it has the opposite argument. negative theta when the original has an argument of theta. Why is that useful? Well, what happens when you multiply two complex numbers? When you multiply the moduli and you add the arguments. Since we're adding the arguments, we just have theta and minus theta. Add them together, you get 0. Zero argument, what does that mean? A zero argument means the complex number is a purely real number. In fact, it says something a bit stronger than that. If you've got a zero argument, you're not just looking at a purely real number, you're looking at a purely real non-negative number. Because an argument of an argument of pi would be a number like -2, for instance. That has an argument of pi because you'd have to turn half a turn, pi radians, anti-clockwise from the positive real line. An argument of 0 suggests that we're dealing with a positive or at least non-negative real number. In fact, technically a 0 wouldn't have a defined argument. We'd say the argument is undefined if the complex number itself is 0. You can see on this bottom line now, we've looked at alpha times alpha star, and we know that we multiplied the moduli, so we've done r times r, and we know that we add the arguments, so we've done theta add minus theta. So we get r squared times cos 0 plus I sine 0. Of course, sine 0 is 0, so the imaginary bit disappears. Cos 0 is 1, so we get r squared times 1. And that r squared, you might remember from before, when we calculated this with the rectangular form a plus bi, out popped a squared plus b squared when we multiplied two complex conjugates. And that's exactly the same as r squared. That's how we calculate the modulus. We use Pythagoras. R squared equals a squared plus b squared. And that's why when you multiply two complex conjugates, you always get not just a real number, but a positive real number.